All right, definitely got a wealth of questions over the break. So I'm going to start with the email ones first, then I'm going to move on to the chat ones. So email, first one comes about the mechanism on page 20 for the Orgo 2 packets. And you're starting with this compound. I'm going to draw it. And close. Yeah, that's it. And you're being asked to come down to this one here. And so students sent me the reaction mechanism. So I'm going to go through what they've drawn. For the most part, what's written here is correct, but there are a couple little nuances, particularly with the ring closing with the benzene, that I'll need to talk about. So the first step, student proposed ozonolysis. So the ozonolysis, we're going to clip this bond here, and I'm going to kind of draw it out. The way they have it written, I understand why they wrote it the way they did. It's just going to make this a little cramped. So with the ozonolysis, we have 1, 2, 3 carbons, 1, 2, 3 carbons. This will come down as an aldehyde. We have 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, and this one breaking off here as a did I draw that right? Yeah, that's drawn right. All right, so next thing they said to use was Jones reagent, and I agree with that. So with Jones reagent, we're going to use chromic acid. I'm just going to write Jones here. And the only thing this is going to do is convert this to carboxylic acid, which is what we need. Now, they use SOCl2 for the next step. I agree with this, but they're putting the chlorine here on the carbon, and I don't agree with that. So for the next step, what we're going to do is we're going to convert this carboxylic acid into a acyl chloride. Hopefully you can see that. Got too many screens open right now. Yeah, so we convert this, and of course, like the light's in the way. Not much I could do for the light this morning. So there's a benzene ring here, and we've got now the AlCl3 will end up coupling. Where did I get off? Oh, okay. Now I know what I'm doing wrong. Could not for the life of me figure out why the carbon moved. Okay. So you have 1, 2, 3, 4, 5, 2, 3, 4. And then branching off this one, we have 1, 2 carbons, 1, 2. And then, again, that's going to be the aldehyde. The Jones reagent will turn this into a carboxylic acid, OH. Our thionyl chloride, SOCl2. I know it's a little cramped. Let's see here. Too much going on this board. Okay, back up. So ozonolysis is going to clip this double bond. We have 1, 2, 3, 4. 1, 2, 3, 4. This will give us the ketone from there. And this will break off as an aldehyde, and then Jones reagent will convert the aldehyde to a carboxylic acid. Thionyl chloride will convert this into a Cl, and that's where your FeCl3, your Friedel-Crafts acylation will give you this product. And I know I keep losing track of carbons in here, but that's ultimately what you end up with doing. Again, I'm just losing track of carbons this morning. And so that will couple this carbon to the benzene ring. And so that's how we get this ring. And this is just the tail that hangs off it doing the ozonolysis of that end. So person who sent me this answer, you're right, except for you put a chlorine on the benzene ring. That's not what happens. The thionyl chloride converts your carboxylic acid to an acyl chloride, and then that acyl chloride is what's going to couple to your benzene ring. page 23. Seriously. Okay, so this is going to be another one. It looks like it's going to go through a Friedel-Crafts mechanism. Where is my rag? Playing the board. Guess we're just drawing this. Oh, there you are. So you start out with the benzene ring. And what you ultimately want to finish up with is this ring here. And this is going to come backwards from a Friedel-Crafts alkylation. So first thing they did, and this is a good thing to do, is they ran it with ethylene glycol. And this is going to create the hemiacetal. We do need to do this because what we're going to do next could potentially break apart, could react with the ketone. Now, what they did next was they hydrolyzed this with H2O to give the alcohol, and then they used thionyl chloride to go with the alcohol. You honestly don't convert the alcohol. So let me write what they've got up here. So they did H2O acid. And hit this with SOCl2, and you keep putting chlorine on the benzene ring. Thionyl chloride doesn't put chlorine on a benzene ring. Thionyl chloride converts alcohols to chlorides. On top of that, you don't actually need to do that. You can go straight to the alcohol, so HCl, or the straight to the chloride. And then if you do your AlCl3, this will couple you to the benzene ring. And then you just need to deprotect your ketone, and that'll get you this product. So I agree with everything, but again, SOCl2 does not put a chlorine on a benzene ring. It converts an alcohol to a chloride, and then your AlCl3, that's going to do the Friedel-Crafts acylation, or alkylation in this case. All right, and the last question, page 21 in the study packet. So okay, so for page 21, there's actually needs to be a correction made to the molecule that's being used. Dia actually brought this up, that if you look at it, I think there's a carbon missing. So if you look at the key, you'll see the spirit of the problem. But yeah, there's definitely a carbon missing between the molecules. So what was supposed to happen here, I'll draw the big molecule. So what was supposed to happen is that you're supposed to use ozonolysis to open this up. So we have a 1, 2, 3, 4, 5, 6, 7, 8, 9 membered ring. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And then you end up with this monstrosity. And then you do something like a Mazinga reduction, which will take off these, so followed by HClZn. Now, if you look at what it's asking you for, it's not a 9-member ring, it's an 8-member ring. So actually what this molecule was supposed to be is this. So it's just simply building the problems. An extra carbon was tacked to the starting molecule. So if you're curious where the extra carbon came from, it's because these are from the molecule you were given would actually end up putting an extra carbon in this ring because it has an extra carbon. This was actually supposed to be cyclobutane, and this cyclobutane will give you what the key has, which is an 8-membered ring with the benzene rings hanging off. But that's all it is, 2-step ozonolysis to cut the double bond, and then a Mazinga ring reduction, HClZn, to get rid of those ketone groups. All right, so that was the email question. Now to go through the questions I've been chatting. So can you explain the mechanism of the first and third compound on page 9, first, second, third compound, page 10. So first and third. So the first one, page 9. So the first one, page 9, this is just a Friedel-Crafts acylation. So you need to go back to the test 1 material. Two, three, four. More. So with Friedel-Crafts acylation, you have an acyl group. It binds the acyl carbon to the benzene ring. In this case, it's going to be the closest because it's going to end up giving us a 6-membered ring. And so that's that mechanism. So again, it's test 1 material for reactions of benzene, and you're looking for Friedel-Crafts acylation. For the second one, this is just a dehydration reaction. So step 1, we have this diol. Your Jones reagent, okay. So the first thing you're going to work with is a Jones reagent or a strong oxidizer. So we'll work with chromic acid, Na2Cr2O7, H2SO4, and water for good measure. And what this will do is it will convert it to a dicarboxylic acid. And then the next step is a strong dehydration. So probably working with very concentrated sulfuric acid here. And what this does is an internal reaction within the molecule. So this oxygen will hit that carboxylic acid, it'll pop off the OH group, which will take the hydrogen off the OH group that's attacking, and we end up getting the anhydride. So just 2 steps. The first one converts to a carboxylic acid. The second is just water removal. And this dries, basically, it looks like an esterification just between 2 carboxylic acids. Again, this OH attacks the carbonyl carbon, gets rid of the OH. This OH pulls the hydrogen off of this oxygen, and we just end up with the anhydride. Page 10. All right, so page 10. First, second, third compounds. So the first compound. So the first 2 steps, the B2H6 diglyne and the NaOH H2O, H2O2. These are hydroboration oxidation. This is organic 1. This is an anti-Markovnikov addition of an alcohol. So end up producing the OH here. The next one, H2SO4, Na2Cr2O7, H2O. That's just Jones reagent. And your Jones reagent converts secondary alcohols into ketones. And then the H2O here is just going to be hydrolysis of the ketone to give you the diol, the vicinal diol. So in this case, the oxygen attacks the carbonyl carbon, kicks up a lone pair to the oxygen. That oxygen will pull hydrogen off the water, and that's how we end up with the OHs. Second one, ooh, I like that one. So for the second one, step one, this is going to be Jones reagent, that's the chromic acid, and this will end up converting this to a carboxylic acid. Next step will be a strong drying agent like H2SO4. Now we're not going to get elimination here because, well, I mean in principle we could get some elimination, but we're looking for a strong driving force here. We're going to look for something that basically pulls the water out of this mixture. And what will happen is that this alcohol will attack the carbonyl carbon. This will break off the OH. This OH will pull the hydrogen off, and that's how you end up with this compound here. So these two carbons are here. That oxygen came from that one, and that carbonyl came from that carboxylic acid. Okay, 3. There's 2 approaches to how to do this, but basically you're going to be attacking carbon dioxide. So however you choose to do it is up to you. One is to start with chlorine and then add lithium. The other is to start with bromine and add magnesium. In both cases, what you're creating is an organometallic. And the reason we need the organometallic is because we're going to react both of them with carbon dioxide. So what will happen is that these carbanions, because these are really truthfully just carbanions. Both are going to attack the carbon dioxide, and they're going to give you the carboxylate ions. From there, we're going to hit this with a little bit of acid to give us back the carboxylic acid. So I'm just going to write the H's in here. And then we're going to do this under very dry conditions, H2SO4. And this will give us the anhydride again. So basically, this one here, the third one is... Oh wait, that's the fourth prop. Oh. For the next one, it's all the same idea, but in this case you would use, so, sorry, this was the fourth one on the page. The third one basically looks like the second one, but there's an OH group on it. So you just take your synthesis from question 1, from question 2, you go to question 3 with that product, and then you use sodium borohydride. The reason why you don't want to use lithium aluminum hydride, it'll cut open this bond. So sodium borohydride is just soft enough to crack that open. I'm going to guess that's what the key says. Four, 5, 6, 7, 8, 9. Oh, I like that a lot better actually. Okay, so for the next one. What will happen here, the PDC or PCC will actually give you an aldehyde. And then what will happen is that this aldehyde will attack, particularly under dry conditions and high temperature conditions. The alcohol will attack this aldehyde. The driving force here is this formation of the 6-membered ring. and then there should be some acid written in there, but the acid write-up will give you the alcohol. So instead of the first one where you created a carboxylic acid and did this nucleophilic substitution, in this case you're forming an aldehyde instead, and that'll finish you off with an alcohol. (11, 12, 13, and 14). So with all of these, you're going to start out by doing the protecting group. The big reason being is that everything you're reacting here is going to go after that carbonyl carbon. So for this one, you start out with the EG, the ethylene glycol. That will give you the hemiacetal. And then you're trying to form the cyano, so you would just do KCN. I would actually start that off with fossil chloride, followed up by KCN. This is definitely back to Orgo 1. This is an SN2 substitution. And then you would deprotect under, I believe it's basic conditions, and the deprotecting would get you back to that. That's pretty much how all these go. So I'm not going to go through all these mechanisms because a lot of these really are just kind of like mechanisms from previous pages with the protecting group added in. So for the next page, you're asked to go with this molecule. You go with the protecting group. And now is when you start doing the chemistry. So you just kind of ignore this as an R group now. And for your OH group, for this one, you would I would refer to the SOCl2, and then follow this by lithium. This will give you the organometallic. Hit that with CO2. That'll give you the carboxylate, and then you hit that with a little bit of acid, give you the carboxylic acid. Yeah, that's pretty much all they are, just protecting the ketone, changing a functional group, and then finishing up the reaction. Page 15 and 16. So you have your nucleophile and you have your final molecule. So in the notes there is an organization. Okay, so the question has been asked on page 15. There are table. Okay, it's 15 on that. Good, it's 15 on this one too. So it gives you a nucleophile, so it's some carboxylic acid derivative. And R prime here is the potential leaving group, and you're given an alcohol, a thiol, and a hydroxide. So what we're looking for here is the stability. So if you go in the notes, there's a table of stabilities for the different carboxylic acid derivatives. The least stable is the acyl chloride. The most stable is the carboxylic acid or the carboxylate ion. And then you have degrees of intermediate degrees. So you have the amines or imides, esters, and so forth. The reason why this doesn't react with the alcohol or the thiol is that it's the second most stable carboxylic acid derivative. So making this thiol ester, or making the ester itself, these are all less stable than the amine, so there's no driving force to convert this to these two. Whereas reacting under basic conditions, that will definitely give you the carboxylate ion, which is the most stable. So it's a matter of what you end up with. If you end up with a carboxylic acid derivative that's more stable than what you start with, the reaction will occur. So everything reacts with an acyl chloride. But in this imide, in this case, it's so stable, the only thing you can react it with is a hydroxide to give you the carboxylic acid, because ultimately that's the most stable form. Like, there's nothing more stable than a carboxylic acid. Compounds, pages 19, 20, and 21. So 19. As the key explains, the first step here is the ozonolysis. This will decompose it, and that's why it's written the way it is to make this a little more obvious. So you'll end up with this compound. Oh, I think it rotates it actually. Then if you do like a Jones reagent, so if I throw in the Jones reagent, this will convert this to a carboxylic acid. And then if I do sodium borohydride, NaBH4, NaBH4 is not strong enough to reduce this to an alcohol, but it will reduce this one to an alcohol. And so I'll end up with that compound. So 20 I worked earlier. 21 I worked earlier. '22. Ozonolysis will cleave this to give us cyclohexanone. You have your choice of reducing agents here: hydrogen platinum, NaBH4, LiH, LiAlH4. H2PT is pretty cheap and easy to run, so this will give you the alcohol. And then you can do an acid catalyzed ether synthesis. So just ether. So yeah, break this apart to give you the cyclohexanone, reduce it to give you the cyclohexanol, and then just use acid catalyzed ether formation to give you that dicyclohexyl ether. '23, I also went over. Page 15. Ansky shows H are removed when the OH is added in the last column for the problems. It would be wrong to include it and have just OH and not remove the H. I'm not going to nitpick on that. You are technically forming carboxylic. So when you react all of these with, so let's say you have your carboxylic acid derivative. R prime is your leaving group, and you throw a hydroxide on here. Typically this R group wants a hydrogen. So when you run the reaction, you'll get an OH. And R prime, because this is negative, we got conservation charge. Whatever the leaving group is, be it an NH2 minus, an SH minus, an OH minus, an alkoxide minus, they're all going to be better bases than a carboxylic acid. As its name implies, the carboxylic acid is an acid. So it will pull off the hydrogen, and technically you're going to finish with a carboxylate ion and an HR. That said, it's kind of nitpicking to take off for that. I mean, you would technically be wrong because you haven't run an acid workup. That's not the point of these problems. The point of these problems is to understand like which of these carboxylic acid compounds break apart when they react with like an alcohol or a thiol or a base. So yeah, I would say you're not wrong to leave the H on there. It's kind of, I mean, you are technically wrong, but I would never take off for it because it is just kind of nitpicking. Example 2, column 1. Where does the hydrogen attached to H3CO go to? It will probably end up going to whatever the leaving group is. So there's two ways you can attack this molecule for the second example. You can attack here, or you can attack here with your CH3, and it's going to be your oxygen that attacks. So in this case, because this is a neutral molecule, that H is going to end up on the carboxylic acid. So if we attack the left side, the hydrogen is going to end up leaving with this carboxylic acid. If we attack the right side, the hydrogen is going to leave with the other carboxylic acid. So this is one of those ones that we have a neutral molecule. We should finish up with neutral molecules. The hydrogen just ends up on the carboxylic acid. Page 15, one of the problems converted ester into carboxylic acid, but why does it work for this and not thiols? How does that work? So we're talking about relative stabilities, but being relatively stable and being like, I don't want to put this. It's not binary. So there's a spectrum of stabilities associated with these molecules. And so if we look at this ester and we hit it with hydroxide and we get the alcohol versus an acyl chloride. And why does the key seem to claim that you can take an alcohol and make it into an ester, but I never say like, well, you can take a carboxylic acid and make it into an acyl chloride? And the reason is stability. So if we look at this, this is actually a reversible reaction because if we look at the energy difference between products and reactants, there is an energy difference, but it's not like a massive energy difference. Whereas if we look down here, it's a purely irreversible reaction because your acyl chlorides are super unstable, whereas your carboxylic acids aren't. So for any given carboxylic acid that we would produce, so at the very bottom of the well, let's just do acetic acid. So at the bottom of the well, we have acetic acid. And we look at the energy of the starting reagents, and if we start with an amine, it's slightly less stable than the carboxylic acid. But keep in mind that dipeptides, so your body is composed of proteins. Proteins are polypeptides. Polypeptides are formed by having nitrogen's bonds to these react with carboxylic acids. So they connect to the nitrogen-carbon groups. That's how they polymerize. So even though amine is more stable, this is less stable than the carboxylic acid. It's not so much more unstable that you couldn't like make it. If we go up to the next one, I think it's the ester. The ester, again, is less stable than the amine, and it's less stable than the carboxylic acid. But this isn't like a huge barrier. This is actually reversible. But if we go to something like an acyl chloride, the energy drop is so big between the starting reagent and the product, this is effectively an irreversible reaction. So it more just kind of boils down to stability. These lower derivatives, the more stable derivatives, they're actually room stable. So you can buy esters shelf stable, and they will slowly react with water over time. But we've worked with ethyl acetate in the lab, and the structure of ethyl acetate is this. You use it for all your TLCs. We can store this in the room just fine. It won't decompose into a carboxylic acid and ethanol because even though, yes, the carboxylic acid is the more stable form of this, it's stable enough that it's not going to fall apart in the presence of water in the air. Whereas your acyl chlorides here, we have to work with them air free, and we actually have to make them from thionyl chloride, which is also not shelf stable or water stable, so it has to be stored specially. So again, it kind of we're kind of looking at when we talk about these reactions, particularly when we're converting amines, esters, things like that. We typically have to punch them really hard to break them down into the carboxylic acid and vice versa. We usually the bigger barrier is actually the activation energy more than anything else. So yeah, I can see your confusion because we say, well, they should react and they should form this. It's like, you're correct. That statement is correct. It's also correct that they're low enough energy that if you just kind of heat them up, you can reverse the reaction. Page 15, column 1, last problem. If the ester is the original compound and when reacted, if the same ester is produced for a completely different ester form, will the reaction still occur in that scenario? So yes, it would occur, but it would be one of those like net sum games of zero. Macroscopically, you wouldn't see the difference. So in this case, you've got an you've got this reacting with methanol, but let's say you reacted with ethanol, it's the same. Would they react? They would, just nothing would happen. You wouldn't see a difference. But yes, there would technically be a reaction. And when you throw the methanol in here, you would probably have a fair chunk of this left just because there's not a strong driving force between the ethyl version versus the methyl version. Will this also apply to other examples that are not esters, but something similar like this? So yeah, if you had a thiol and you had a methylthiol versus an ethylthiol, they self-react. It's just you probably wouldn't ever see it. And again, for these particularly more stable esters, you may not even get a reaction at all because you have to hit them pretty hard to make them to react. Page 13, would it be wrong to add the H plus to remove the ethylene glycol after adding lithium? Yes. So if you add lithium, you're forming a carbanion. So that's really what the lithium is. If you add an H plus, this would immediately react with it. And so this is why things like Grignards and organolithiums are always run air-free, water-free. As long as you've got an organometallic, you cannot have a hydrogen source. So you can't have any protons accessible, otherwise it'll react it away. The key shows ethylene glycol removed first and then lithium added. I understand this, but why does it matter? Does it really matter in the sense as to which order is completed? Let me bring up the key on page 13. Use ethylene glycol to protect the ketone. Use KCl to make the alkyl halide. Next, deprotect the ketone and add lithium to make the organometallic, which will attack the ketone. Follow this by an acid workup. So yeah, the order here is going to matter. Because the goal here is to create, so I'll write up the problem. So first step is to protect. And it says use K. So we're going to protect it with KCl. We're going to protect it. And then we're reacting with KCl. The big reason we don't want to react with KCl by itself, this could definitely attack the carbonyl carbon. And then if there's acid present, you'll end up getting basically the alkyl halide, you will get an alcohol that's also an alkyl halide. So we have to protect this group. And so we add KCl, we heat it up, this will give us the chloride. Next we add the lithium. The lithium converts this to a carbanion. And now we want to deprotect the ketone. Wait, Make the alkyl halide. Next, deprotect. Oops, sorry. Next, we're going to deprotect. And we need to do this because our method for deprotecting will actually react with the organolithium. So now we can make the organolithium. This is our carbanion. It will attack. It'll give us our ring, and then we do the acid workup. I'm glad to hear that. KQ is 0.19. What is delta G at 125 degrees C? I did get 2.29, but sig figs is 2.30. Let me bring up Excel. So KQ is 0.159. And we have that delta G naught equals minus RT ln KQ. R is 0.008314. And temperature here is, since you're given 125 degrees 7, that'd be 398 Kelvin. So equals minus 0.008314 times 398. Natural log of KQ. So I'm not getting 2.298. When I run this, I'm getting 6.08 kilojoules per mole. My guess is that you just use the 125. So I'm not sure where you're getting 2.298, because even using 125 degrees C instead of 298 Kelvin, I'm getting 1.91. So my guess is that you're not taking the natural log correctly. So about 2.298. I'm not sure where you're getting your numbers from, but it should be if you do the 398. Come on. You're going to get 6.08. Schemes on page 21 and 22. So this is going to be organic 1. Okay, so 21. So 21 versus 22. Wait. Starting molecule is this, and you want to go to this. So the big thing here is that this is going to be an E2 elimination. If we did an E1 elimination, we'd have a carbocation. So we could do something like H plus. This would give us a carbocation. We get carbocation rearrangement. And then when we finished off the elimination, we'd end up with this alkene. To promote an E2, we want a basic salt. We want to run this under basic conditions. So something like tert butoxide. This is a pretty big aggressive base. And we would want to run this underneath a pretty low dielectric constant solvent. Honestly, your tert butanol will probably work just fine for this. This is a pretty low dielectric constant on its own. But if you compare this to the example on page 20, 20 is the E2, E1 mechanism. So this route. And this is going to be the E2 concerted mechanism. And that's all this is really trying to test you on, is like recognizing the E1 versus the E2 product. For page 22, this is also going to test your knowledge of an SM1 versus SM2. There's actually two ways to do this one. I would recommend, if you look at the discussion boards talked about which molecules are inherently stereospecific. Actually, there's a lot of ways you could do this one. So the easiest is SOCl2. Thionyl chloride is very stereoselective. It always inverts the symmetry. So you would end up with this. You could do tosyl chloride and then use a chloride ion, so NaCl. That would give you the same effect because this is selective for SN2. The other option is that you could run NaCl under something like THF, a very low dielectric constant solvent. But in all cases here, you're trying to basically drive an SN2 mechanism to get that type of inversion. So I don't have a page 26. I think you're looking at the solution packets. Let's see here, 21. This is test 3. I don't have a page 26 on either of the study packets for organic 1 for test 3. But that said, I can do the homework if you can just give me the page numbers. For the homework, I'm going to need to log in. All right, number 6 and number 15 on the homework. Did I post a revised copy to the course website? Good question. So I've only got 24 pages in even the new packets that are for next semester. There's only 24 pages. So I'm not sure what's going on. So I have what I loaded to the course website, and they're only 24 pages long. But let me do the homework for you. If you could tell me what's reacting, I can probably figure it out. Draw the formula for sec-butyl alcohol. I hate that we have to teach like these non-IUPAC names, um, but there are some like isopropyl you do need to know. They're used pretty commonly. The way I remember sec-butyl, the sec here is secondary. So the second carbon is going to carry the alcohol. So that's sec-butyl alcohol. You would prefer to call it 2-butanol or 2-butanol. That's the IUPAC name. But because sec-butyl predates IUPAC and was pretty commonly used, it just shows up a lot. So again, I just remember sec-butyl as secondary butyl, and it's a butyl 4-member carbon where you're attaching to the second carbon. Number 15. Name the following compound according to IUPAC's substituted nomenclature. So, a fun example early on about how IUPAC will ignore its own rules. So we have this compound. And when we named alkanes, we would always start with the alkane, the longest chain being the primary. Now we're going to put the alcohol in the primary, even if it ends up being the shortest chain. So we have a 2-carbon chain here. So our parent here is ethanol. And we're going to have to specify that it's 1 ethanol. But we have a methyl, a cyclopentyl. So 1 methyl, 1 cyclopentyl ethanol. Oh, you're annoying. Okay, sorry, no. My mistake. We're going to treat these 3 carbons, so this ends up being propanol, 2-propanol. So it's 1 cyclopentyl, 2 cyclopentyl, 2 propanol. So even though this 3-carbon chain is shorter than the 5-carbon, it's just easier to name it this way, so that's the way we're going to do it. We've got 3 carbons, that gives us the propanol, so it ends up being 2 cyclopentyl, 2 propanol. And that's it. Um, 26. It is a 2-ring compound with chlorine that goes through 2 schemes. One replaces bromide, the other eliminates. So let me bring that up. And also if you have the section name. So is it synthetic schemes or is it synthesis with characterization? It's 7-cyclohexyl 4-heptanol. Simple synthetic schemes. I am trying to find it. All right, to answer another question really quick, how do I find KSP from concentration? So you need your ICE table, and you need your expression for the reaction. So you have KSP equals Q. You will have your IC table. And from the problem, you're going to be given at least one equilibrium concentration. You will probably have to use whatever equilibrium concentration you were given to figure out the extent of reaction. And from there, you'll figure out what the other concentrations are. Once you have all the equilibrium constants, you plug them back into your expression for Q, and that's how you find KSP. Seven cyclohexyl 4-heptanol and aspartame. Yeah, if you could, because I'm not seeing them in this packet, which is weird because I should have them. Yeah, just send me pictures of them. I'm not seeing them in these packets I have, but I may just not be looking in the right place. Weird. All right, so that's it for office hours. Again, if you ever have questions, please feel free to email in advance. Sorry about not being able to find that problem, but yeah, if you send me an email, I'll definitely try to respond to you about like how to answer those questions. All right, I will see several of you tomorrow for the exam for Chem 2, and I will see several of you tomorrow morning for lab.